Okay, this video is going to deal with phase change calculations, and it's the first video out of two, so be on the lookout for another one coming up shortly. So this one's just going to continue with our kinetic theory that we've been learning about in our energy unit. So we're going to start to apply this a little bit in the form of calculations. To get us started with that, we need to know a little bit about some of these boundaries. So we are probably very familiar with solid liquids and gases. And if you recall, if you increase the temperature, you're increasing the kinetic energy. So imagine, if you will, that you have a solid block of ice and you're starting to heat it up until it gets into a liquid phase. This is what we call this boundary here, the heat of fusion. We need to increase the amount of energy to get past this barrier to pull it into the liquid phase. The same is true with this heat of vaporization. You probably have noticed it takes quite a while and you're waiting patiently for your water to boil and it's bubbling up, but it takes a little bit longer for it to start to escape in the form of gas particles. This is what we call here the heat of vaporization. And just looking back over this little diagram that we had looked at earlier, as a review, if you see gas going into a liquid, that's condensation. You may see this in the morning when you go outside and look at some of the plants. The gas is going directly back into that liquid water that you're seeing on top of the plants in the form of dew. Liquid to gas, we had just mentioned that with water, just waiting for it to boil off until it starts to vaporize. Solid, if you let a piece of ice come out into the room temperature, it'll start to melt into a liquid, and then if you take that same liquid and put it into the freezer, it'll go to a solid. Gas going to a solid is an example of deposition. You may have to increase the energy or pressure for this to happen. And sublimation, you may have seen this. It goes from a solid to a gas, and a good example of this would be dry ice. We've seen, many Halloween parties where people will just take a big block of dry ice and throw it into their swimming pools, and just it's all spooky with the gas coming off the whole time. It's a fun little exercise. So let's look at these in detail. Once again, evaporation is the process by which the particles of a liquid form a gas by escaping from the surface. And if we look here at this diagram down below, you'll see, for example, that this one has probably been a liquid that has been heated to the point where the particles are increasing in kinetic energy and they're starting to get to the point where they are releasing into a gaseous form. And if we were to look at this Boltzmann diagram that we had talked about in the last podcast, you have a certain amount of particles of some water and you're increasing the kinetic energy, which of course is going to increase the speed. And this is where the average amount of particles will lie at this temperature. But as it's continuing to heat up, the kinetic energy is starting to heat up, the faster it's starting to get. And these are the particles that will start to evaporate off. So this is the minimum kinetic energy to escape the surface of a liquid line right here. So everything before this line is not going to escape, and everything beyond this line will start to escape. Liquids that evaporate quickly are called volatile liquids. That doesn't necessarily mean that they are flammable. Yes, most volatile liquids are flammable, but let's think about the case of alcohol being applied to the skin because you want to get it prepared for a shot or something of that nature. You will notice that the alcohol will rapidly evaporate from the skin. That's considered a volatile liquid. Now, vapor pressure is the pressure of the vapor above a liquid. An example of that, let's go back to this diagram here. This is heating up, and as these particles are colliding off to the little flask here, it's creating pressure. So this is the vapor pressure above the liquid right here. And notice that it's being trapped right now with a cork or a stopper. Now, the boiling point is the temperature at which the liquid's vapor pressure equals the pressure exerted on the surface of a liquid. Now, what that means is if you have, let's say you're at sea level and you have 1 atmosphere of pressure pushing down on you, which is about right, then the liquid's vapor pressure in this example would be at 100 degrees Celsius. Conversely, if you were to look at, let's say, Denver, Colorado, which is about 8,000 feet above sea level, they only have about 0.8 atmospheres of pressure. Therefore, their water temperature will boil at a lower temperature, maybe around 90 degrees Celsius. And it all has to do with the temperature at which the liquid's vapor pressure equals the pressure exerted on the surface of the liquid. Going back to condensation, we already said that was the reverse of evaporation. It's whenever the vapor condenses back into a liquid state. Sublimation, once again, is the process by which the solid escapes from a surface and will go directly into a gas phase. Think of that dry ice that we talked about. Its opposite is deposition. That's when the gas turns directly into a solid. And to go from one phase to another requires two things. One is definitely energy. Energy is required to raise the temperature to the point where a phase change is possible. Now, sometimes these barriers will, these boundaries will get like a little bit, needs a little bit extra to get them moving. So that's whenever we may need to increase the energy. And each phase change for every substance has a specific energy to change from phase to phase. So we're going to do some of these by way of calculations, and you'll notice water has its own specific energy, and different metals will have their own specific energy, and we'll talk about these later in the form of specific heat whenever we do those calculations. But let's try this one right here. We're going to talk about the heat of vaporization. We're going to go from a liquid to a gas. And we're talking about the energy absorbed when 1 kilogram of a liquid vaporizes at its normal boiling point. So we can use two different conversion factors depending on what unit they give to us. For water, the heat of vaporization is 40.1 kilojoules per mole. Now, we haven't really talked too much about moles yet, but we will, don't worry. Or another conversion factor that we can use is 2.26 times 10 to the 6 joules per kilogram. Well, what we're trying to do here is make this into kilojoules per kilogram, which is probably something that you're more used to. So to do this, we would just simply do our conversion factor to take this by the 1,000 and get this down here to the 2260 kilojoules, which is equal to 1 kilogram. Now we can go and apply this. So if we were to just take any number, let's say our given was 2.5 kilograms, and we apply this conversion factor right here, which is given to us, the 2260 kilojoules is equal to 1 kilogram. We want our kilograms to cancel, if you recall. So you would put the 1 kilogram right here down below, and then we put the 2260 kilojoules up above. So these kilograms will cancel, and after you multiply the 2.5 times 2260, you're going to get 5,650 kilojoules. That's how much energy is required for this particular problem. Now let's look at another one. Let's look at the heat of fusion. The heat of fusion is the energy released as 1 kilogram of a substance solidifies at its freezing point. For water, this is, and we can use one of two conversion factors, 3.34 times 10 to the 5th joules per kilogram, or 6.01 kilojoules per mole. So let's look at this example. How much energy is released when 10 moles of water are frozen? Since this is asking us for moles, we're going to use this conversion factor right here, 6.01 times or kilojoules per mole. So we can get these moles to cancel. These units do not match up with this, so we're going to use this conversion factor. Okay, so we're going to take the 10 moles, which is what our given was. We're going to put the 6.01 kilojoules up above per mole down below. And once we do that, these moles will cancel out, and we're going to be left with 60.1 kilojoules. That's how much energy it's going to require for this heat of fusion problem. So now let's just look at a couple of these heating curves here. Heating curves, this is a heating curve for water, and you're probably fairly used to these from prior classes. Oops, I moved them around, and now these aren't going to be matching up very well anymore. But notice down here, I should probably just put it back where they were. No, I'll just move my arrows. Okay, so with this one here, notice that this line right here is our freezing point, and this is our boiling point. And whenever you're seeing these slopes, that's an actual change in temperature. So notice here, this is minus 20 from 0. That's a temperature change right there. And then the freezing point, here's another temperature change over time. Okay, and then the boiling point, like we said, it can take, a pretty lengthy process. Notice it looks like it's almost about 15 minutes or so here. And then it's going to go into the vaporization part right down here. Now, if it's going up to the right, that's indicative of a heating curve. And conversely, if it's going to down to the right, that's indicative of a cooling curve. Okay, again, the slopes represent temperature changes, and these are the actual boiling and freezing points. So this is just to kind of look at it a little bit more blown up. Once again, the freezing, boiling, temperature change. This is the heating curve for water. Okay, so we're going to do a couple calculations to help you out with these, and then this will continue on to some further calculations on our next podcast.